By now, you should hopefully be familiar with how you can describe the complexity of an algorithm. Specifically, you should have learned that there's three common notations people use: big O notation, big theta, and big omega. So for example, let's imagine I have the computational problem, find the largest number in a list. The input is a list of numbers, and specifically the length of that list is n, so it's a list of n numbers, and it's called x. And the output is a number v that exists within x, so one of the numbers in x, such that that number v is greater than or equal to w for all numbers w in x. So basically, return some number v that's greater than or equal to all numbers w in x, where v also is in x. This is a formal definition of this computational problem. Here we have two algorithms that attempt to solve this problem. So in this first one, for each number v in x, assume that it's true, and then for each number w in x, if we ever run into a number w such that v is less than w, that means that v was not my maximum number. Therefore, we say, nope, it's not the best. And then after we've iterated over all of w, if best is still true, so if we never encountered a number w such that v was less than w, we return v. V is guaranteed to be the largest. On the other side, we have another algorithm that attempts to solve this problem. We start v at negative infinity, and then for each number in x, so for each number w in x, if v is less than w, set v equal to w. And then after this loop is done, return v. It turns out that both of these algorithms provide a correct solution to this computational problem. I won't formally prove this, but it should hopefully be clear just by how simple this problem is. However, what is the time complexity of these two algorithms? This one, for each of my big O of n numbers, I do a big O of n traversal for each of them, not like iterating over the numbers next. And then within this inner traversal, I do a constant time comparison and potentially a constant time assignment. So for each big O of n numbers, I do a big O of n loop. That means that this one is big O of n squared. What about this one? I initialize, which is constant time. Then for each number in x, so for each big O of n number in x, do some constant time comparison and some constant time assignment, potentially, and then a constant time return. So I'm only doing a single big O of n iteration over my list. So this time complexity is big O of n. So same exact computational problem, two different solutions that both do indeed provide a correct answer to my problem, but they have two different time complexities. So this is how I can describe the complexity of an algorithm. But what about the problem? What if I wanted to describe the complexity of the problem itself, regardless of any specific algorithmic solution to the problem? We will discuss various classes of computational complexity that are used to describe computational problems themselves. Not solutions, but the actual problem.